Okay, so it's my pleasure to introduce Stefano Camera. Stefano Camera is a cosmologist. He has an associate professor in Turin. He got his PhD in 2010. Then he went to University of Lisbon as a postdoc until 2014, right? Then he took a very bad decision. Instead of accepting the offer we made him to come to Saclay, he went to Manchester. Can you imagine? And nevertheless, he got a permanent position a couple of years later, 2017, in Turin. And he's involved in two of the biggest projects in astrophysics and cosmology. One is Euclid, the space project doing for weak lancing. And the second one is SKA, the square kilometer array. And Stefano is going to introduce us the synergy between these two projects.
Thank you, Jean-Luc. Let me, if I ever manage to get these things out again. There we go. Thank you indeed. Thanks everyone for being here. It's really, I mean, everyone always says it's a pleasure to be here, but it's really a pleasure. This is my first time in Greece at all, in this beautiful also institute, and I'm really happy to have managed finally to come visit Jean-Luc and talk about some interesting science. Yes, I did foolishly not accept his offer, but I mean, we've been keeping contact over the years, and hopefully something will come out in the next years about these synergies in the radio and in the optical, which is basically what I'm going to talk to you about. Just as a reference, since I understand that the audience is broad and not all of you are cosmologists, does this? Okay, yes, it works. Just a quick sketch of what's our current understanding of the universe, which is what we call the Coordinates cosmological model, or Coordinates cosmology, is just a setup of all the models that we've put together to describe the universe. And well, we've always looked at the sky and the universe in terms of light, in terms of stars, and then later in terms of galaxies. And now we know that these stars that make up galaxies are only about 7% at most of what's present of luminous light, and the rest is in the form of gas in galaxies and clusters. But this is not enough, because the real deal is that at the end of the day, well, all of this is just what we call ordinary matter, what we know, the standard model of particle physics. This only accounts for 5% of the total energy budget of the universe today. The rest is in the form of some mysterious dark matter, which represents the scaffolding upon which, or if you want, the roots upon which the ordinary matter in the universe is distributed, and we can see it. And this is roughly, altogether, matter is about 30% of the content in the universe. And today, the rest is in the form of some mysterious form of what we call dark energy, or could be just cosmological constant, but still something which is driving the current day, present day accelerated expansion of the universe. Now, if you want to summarize the cosmological model, it is a very, very successful model to describe an incredibly broad swathe of scales and phenomena and energy and time for the whole history of the universe. But still, there are these main big important questions that we still need to answer. One of them is, of course, what is composing most of the matter in the universe? This exotic type of matter, which we call dark matter, is really some form of new fundamental particle. Is it something different? We have no idea at the moment. We think it's a new particle, but there's only indirect evidence. And then we have two very distant stages in cosmic evolution, both in time and in scale, which are yet remarkably similar. And these are inflation, which happened right after the Big Bang. At the moment, our knowledge of what we call inflation is more of a paradigm than really a theoretical model, because it's a paradigm with a large number of practical realizations in terms of theory, and we definitely need to trim them down to get some understanding of what went on at that time. What we want to do in this sense is looking for imprints. And the CMB community has been looking for a long time on B modes, so some specific imprints due to gravitational waves generated at inflation, and this you could aim at detecting in the cosmic microwave background. And in terms of the last case structure, what people want to do mostly is look for non-Gaussianity, so the possibility of the initial perturbations of the universe being distributed, not perfectly in a perfectly Gaussian way, with some amount of non-Gaussianity. We would like to measure this amount of non-Gaussianity because this is one of the so-called smoking guns of inflation. This would help us ruling out entire classes of model or inflationary models. The other of these stages of evolution that are similar to inflation is dark energy, so the current present-day accelerated expansion of the universe. Is this another mysterious scalar field, or maybe the same scalar field that reappeared? Is it really a seemingly fine-tuned cosmological constant, which is just another constant of nature, like gravitational constant? Or even, is this a symptom, actually, of an incorrect gravitational theory, which we are using to fit data on cosmological scales, but we don't have really any cosmological confirmation of the validity of general relativity the way we have it at the exquisite level in the strong gravity regime, from black holes, neutron stars, and anything else you can think about. So these are the main open questions in cosmology, and what I would like to talk about, and what most people in cosmology are interested in at the moment. The way I'm going to deal with these problems is through the last case structure for the universe, studying the last case structure of the universe, studying it through correlation functions and power spectrum. Again, just a one-slide sketch about what is correlation functions and the correlations we do in cosmology. Consider we have cosmological perturbation, which is inherently a random field, so a random variable with a time evolution which is deterministic, but the distribution in space in three-dimensional position x is random. And this field could be temperature fluctuations like in the CMB, or some density perturbations in the underlying matter density field. This quantity being stochastic, we cannot predict its distribution per se, but what we can predict are the statistical properties of it. And the first one is, of course, the two-point correlation function. So you take the ensemble average of this perturbation into different positions in space, at position x and position y, and given at a given time, which is here like using redshift as a label. And this two-point correlation function, given homogeneity and isotropy, so the cosmological principle, has to depend only on the physical separation between these 2 points. It cannot depend on the orientation because of isotropy. It cannot depend on the position because of homogeneity. And so this is what we use a two-point correlation function. And an example of the correlation function is when you have galaxy distribution. So as first order, you can consider the number density contrast in the distribution of galaxies at a given position and at a given time with respect to the average that you have at that time. This is the galaxy density contrast in number counts. And you can measure the galaxy correlation function in this way. This is a plot from basically the collaboration that measured for the first time what we call the variance acoustic oscillations. You have here, as a function of a co-moving separation in megaparsecs over h, you have the galaxy correlation function for different cosmological models represented by different amounts of matter, ordinary matter and dark matter. And you see the correlation function peaks at very low separation because you have the most of the probability of finding two galaxies near to each other, and then it drops. But there is a bump in this drop that is fit by a particular combination of cosmological parameters, which is the green one, which is basically the 5% ordinary matter and 25% dark matter that I showed you in the beginning, and remarkably is not fit by just dark matter, which is the magenta line with no variance at all. So this is just to show you how we deal with correlation functions and why they are important in cosmology. But then, of course, you can do the same exercise in Fourier space. Here, a hat denotes a Fourier transform of that quantity. And what you end up with is what we call the Fourier space power spectrum, or just shortly, the power spectrum. Homogeneity in the isotropy in this case is translating into having it depending only on the wave number and not on the direction of the wave vector. And well, the example for this is the matter power spectrum. So you have density in some position in the universe with respect to the mean energy density of the universe. And this is the power spectrum that you have. These data points here are from various experiments spanning the whole of cosmological experiments so far. So CMB, Planck, here you see temperature and polarization and CMB lensing in these three first columns, and then you have galaxy clustering and lensing in the other three. But these are not data directly taken on the power spectrum because, of course, we do not measure matter, we only measure other things. So these are reconstructed measurements on the power spectrum. And below you see the matter power spectrum curve from the cosmological concordance model in black. And you don't see them, but here there are wiggles that are related to the Fourier transform of that lamp. So this is the BAO wiggles that are here. Finally, another way of doing correlations is in a more anthropic way, in a sense, not an anthropic in the philosophical sense, but just considering that we are observing the universe at the center as like located at the center of a sphere, and we just look at the night sky and the celestial sphere, right? And we see perturbations of that. So the more natural way to deal with this is decomposing the perturbation in spherical harmonics, because they are the way that you have perturbations on the sphere. This tilde here represents the coefficients of the spherical harmonic expansion of the perturbations. And what you end up with is what we call the harmonic space or angular power spectrum as a function of multiple. Again, being homogeneity in the isotropy translates it into have it depending only on the multiple L and not on the orientation, the azimuthal M. And an example of this is the CMB, cosmic microwave background temperature power spectrum. We are measuring the temperature of the sky today in a given direction in the sky. You translate this into spherical harmonics, and you have this beautiful measurement from the Planck satellite. This is really the measurement of that, so it's been not reconstructed somewhere else. You have angular multiple here, so small angular with multiples means like large angular separations, and the other way around. And these data from the Planck satellite fit by a model with only 6 parameters, which is really truly remarkable. Well, it's something that when I see it always makes me understand why I like cosmology, the possibility of like describing the whole universe with a bunch of parameters this way. So this is the way we do correlations. And then, of course, given that we're talking about 2-point correlation so far, just because to make it easy, you can also substitute, well, one of these Fs around with another perturbation and have cross correlations. Now, you may wonder what's the point of doing these cross correlation studies, given that the cosmological information per se is contained within the variable. So in principle, the amount of information that you have from this cross correlation should be exactly the same that you have from the autocorrelation. The point is that we don't measure directly these things. Our measurements are affected by observational systematics, noise, and even the poor statistical sampling that we have from the fact that we only observe one universe, right? Which we refer to in cosmology as cosmic variance. So there might be instances, and this is what I would like to convey as a message in this talk, where if you carefully select one of these cross correlations, or even better, you use all the information at the same time, you can retrieve some information that would have been otherwise lost because of systematics, because of being buried in noise, because of there being just too much cosmic variance. So the rest of the talk will be split into these 3 different ways of approaching these problems in cosmology, applying cross correlations and synergies. If you have questions at the end of each of them, you can always, you can ask at any time, but even at one of these like definite steps. The way I want to do these cross correlations is using cosmological experiments on the large scale structure. And as Jean-Luc was saying, there will be mainly Euclid satellite and the square kilometer, the SKA observatory. Now it's called like that. I don't think I have to tell you much about the Euclid satellite, being Jean-Luc here. Euclid satellite is a European Space Agency M-class, so medium-class mission, which will be launched in less than a month, which is super exciting and super scary. And the scientific exploit of the data collected by the Euclid satellite is in charge of the Euclid Consortium, which is the network of universities and research centers that are related to this project. This is Euclid in space already, as you can see. But again, the Euclid as an instrument, well, as a satellite, there's actually two instruments on board. One is an imager to do with lensing, another is a spectrograph, a Griezmann, actually, to do spectrography and measure the position of galaxies. And this is all that I'm going to talk to tell you about Euclid, because I assume that you know some of this already. Otherwise, you can always ask. The other thing is the SKA Observatory, and I will spend a few more slides on this. The SKA Observatory is the second intergovernmental organization in the world for science. It was born officially in January 2021 after a long incubation period with many stages in between. The global SKAO headquarters are in Jodrell Bank in the UK, and the SKA as an observatory will be built into different locations in South Africa, in the Karoo Desert, and in Western Australia, in the so-called SKA low and mid sites. Partnership includes different member states with the NASCARs and founders, and partner countries and some interested countries. And there's a network of African partner countries that will develop new science and with the aim of engaging countries in development for the SKA. The SKA project per se, which was formerly known as Square Kilometer Array, will be the largest radio telescope on Earth and will be built in these two locations. So the Australian location, and it will operate between in the bandwidth between 50 megahertz up to 14 gigahertz. The Australian site is the so-called SKA low, because it's the low frequency instrument. It will work between 50 and 350 megahertz with antennas, so with about 150,000 antennas, with a total collecting area of almost half a square kilometer. And with the maximum distance between stations of 65 kilometers. If you want to compare it to the best current similar instrument in the world, which is the low frequency array in the Netherlands, LOFA, the SKA low will be 25% better resolution, 8% more sensitive, and 135 times faster in scanning the sky. The South African instrument instead is it will operate between 350 megahertz, so the end of this bandwidth, up to more than 14 gigahertz, depends on the receivers that will be mounted on top. It will comprise about 200 dishes over a total collecting area of 33,000 square meters, 126 tennis courts, if you're interested in the fun. And the maximum distance, so the longest baseline will be about 150 kilometers. In terms of the current best similar instrument in the world, which is the Jansky Very Large Array, it will have 5 times the resolution, it will be 5 times more sensitive, and 60 times faster in scanning the sky. If you're interested in cosmology that could be done with the SKA Observatory, I can point you to this effort that we did with the SKA Cosmology Science Working Group back in 2020 after a few years of work, which is what we call the Square Kilometer Array Red Book for Cosmology, a technical specification and performance forecasts. And if you're interested in more like futuristic application of the SKA, also in other disciplines of physics, there's this fundamental physics with Square Kilometer Array, which is a review coming after a conference we had again back in 2018 or 2017. Now, before we have the SKA is being built in this very moment, but there are so-called precursors and pathfinders. Precursors are experiments that are located at future SKA sites, whereas pathfinders are experiments engaged with SKA-related technology and science. There's many of them. Some of them you surely know, and in particular, I'm involved with the Australian SKA Pathfinder, ASCAP, Meerkat, which is represents the core of the future SKA South African instruments. It's already 60 dishes operating. And then we have Emerly in the UK and LOFA in the Netherlands. Now, let's move on then to science. I was telling you about how to deal with observational systematics in general, noise, and cosmic variance with cross-correlation. So let's start with Synergies to be systematic. And I will use as a science case shear, so weak lensing in cosmological context as an idea. So the idea of lensing, surely you know, is that light rays from distant objects get bent by the presence of intervening matter on the way towards us. If you look at such a galaxy from Earth, with galaxies all around distributed randomly in this way, what you would observe, even if this is the true position of the galaxy, your image will be something like this, where you have galaxies being stretched and tilted in a way that matches the underlying gravitational potential of the relativity structure. In the weak lensing regime, where these distortions are for 40%, so very small, not the beautiful, strong lensing arcs that you can see and recognize by eye, in the weak lensing regime, these distortions can be decomposed into convergence, so an overall magnification of the size of the object, and the shear, which is a complex quantity that tilts and conserves the area, but just squashes and tilts the orientation of a galaxy, if you consider galaxies like as circles or ellipses. Shear is one of the main targets of Euclid, that has been the targets, for instance, of the dark energy survey, which is an ongoing cosmological survey. And just to give you an idea of how the synergies can work, I'm showing you here the redshift distribution of galaxies expected back in 2015 from the dark energy survey, so an optical survey covering 5,000 square degrees, and in black, the same patch of sky as it will be observed in the radio at the Square Kilometer Array Observatory. And here you see the source redshift distribution normalized to some units. And so, for instance, you can immediately see that the two are comparable and complementary, because in the optical you have much more galaxies, but the distribution of galaxies at a given flux cut drops quite quickly, whereas in the radio you have fewer galaxies, but they are distributed over like longer redshift range. And this is due to the fact that in the radio basically you don't have dust obscuration, right? So you can see much further in redshift. How this translates into observables, here you see the angular power spectrum of cosmic shear as a function of angular multiple, like for the CMB, but by measuring shear position of galaxies in the sky. For the two instruments as before, so pink is optical and black is radio. And you can recognize the features that I was describing in this plot, because lensing is an integrated effect. So the further you look, the more lensing you have, meaning that the magnitude of the signal is higher if you can go higher, deeper in redshift. And this is the reason why the black lines, so you have many lines for the same colors, because this distribution have been split into different redshift bins, right? We do tomography. But you see that overall, the black lines are higher, so there's more power for the weak lensing in the radio because you can go deeper. The other thing is that you have more galaxies in the optical. So the arrow bars on this far right side of the plots are larger for black, so radio, and smaller for optical, because this is shot noise. So the more galaxies you observe, the larger, the smaller would be the arrow bar.
When you say you observe the galaxies in the radio, continuing emission?
It's continuing emission, mostly continuing emission, yes. So this,
and you know the redshift because of spectroscopy?
That's one of the things, right? You need to know the redshift somehow. From continuum per se, you would basically have no redshift information, or very little, if you can, cross-correlate it with some other properties of galaxies. We hope to have some of that information on redshift from SKA, so from H1 galaxies, but that will be for very low redshift in comparison. And then the rest with some cross-matching and other like clustering redshift techniques and similar. But it won't be like spectroscopic redshift all the way to very high redshift. So the way these distributions will be split won't be even.
So right? I understand my question then is sort of if you need to get the redshift from some sort of a significant, how come you don't have galaxies that redshift if you need a galaxy and you don't need to get the redshift? No,
but yeah, okay. At certain point, you can use clustering redshift, for instance, to have a clustering redshift. So the use of use correlations of position of galaxies in the radio with the distribution of other galaxies, which redshift you know, whose redshift you know. to have a cross match on different scales, and you use that as a proxy for redshift. Is another way of doing a redshift estimation. And then the rest will be like some, if not one, large redshift bin at very high redshift in a sense. Now, the way you can use this different complementarity between observations in the optical and the radio is to be systematic. So when you measure the ellipticity of a galaxy, this ellipticity will be due by the intrinsic cosmological signal, which is cosmic shear, gamma, plus some systematic, which might be instrumental or even intrinsic from the signal. Now, if you take the correlation of this, of course, you have your cosmological signal, the thing that you are after, plus all the cross terms and the autocorrelation of systematic. Now, in an ideal world, this cross correlation between the systematics and the signal should drop, at least to some level. But you still need to know your instruments very well in order to model this and remove it from the data, and not to claim some measurement because there was some spurious signal left over. But then if you do the same exercise, measuring the ellipticities in the optical, in the radio, the cosmological signal is the same because lensing is achromatic, doesn't depend on wavelength. Then the cross cosmological and instrumental term will drop as well, but you expect this to drop the same way because these two instruments know nothing of each other, right? One is an interferometer, the other is an optical telescope. So the great power of this cross correlation is just to single out your actual cosmological signal. This we this we showed in a paper back in 2015 and later in the SKA Cosmology Red Book by looking at the error contours. This is a 68% mild confidence region on the measurement of the dark energy equation of state parameters, so the value of dark energy equation of state today, and its evolution in time. So if it's cosmological constant, we expect to have -1 and 0, which is these markers. And this is what you would observe with the stage 4 experiment in the optical like Euclid, in the radio like SKA, and the cross correlation in green. So basically, one thing that you can learn from this plot is that the two instruments are comparable in constraining power because you have basically the same contours, and the cross correlation just singles out the same constraining power in the same way. But this is in an ideal case with no systematics present. Now, if we switch on some spurious residual systematic at the level of 15% of the cosmological signal, what you end up with, what we found in this analysis was that the actual precision of the measurement doesn't change, but the accuracy does. And so you end up with these confidence regions like spread around in parameter space, whereas for the cross correlation, it stays where it should because this additional systematic swap. Now, you may wonder if this works for any kind of systematics. Well, this is just in the case of additional systematics, which is the cartoon that I showed before. If you have some multiplicative systematics like miscalibration of the shear measurement, that of course won't just so easily drop because you carry through all the correlations. But what we argued back in 2015 is that if you use all the information together in blank, so the auto and cross correlation between radio and optical, you can perform some sort of self-calibration where you have this multiplicative systematics and biases that pull and push in different direction in parameter space, so that when you put all the information together, you go back to where you should. So this was just an idea back then, was done in Fisher matrices with no real data or no actual something more specific and more realistic. But then recently, with my student Roberto Ingrao and others, are trying to do this with realistic data in a CMC-like setting. Now, this is a plot that shows to you the marginal errors that you get on the dark matter abundance, so the 25% from dark matter, as a function of what kind of experiments you use. SKA alone, Euclid alone, the cross correlation alone, or the total in black. This should have been switched anyway. And you see that they are comparable, and the total is much better than the sum of the parts. Now, if you just switch on this multiplicative systematics and you do not correct for them, you go all around in parameter space. if you add systematics nuisance parameters that should account for them, you can go back at the price of enlarging your error bus by a significant amount. But if you do this total self-calibration exercise that I showed you before, and this is done with like synthetic data, but still in a realistic setting, it looks like you can get back not as much as it was in total at the beginning, of course, but still a good amount of information that was lost in a different way. So this is just preliminary. This is done for been done for dark matter, and now, of course, in case of the sigma 8, which represents the clumping of the universe, the situation is not as good because this is another multiplicative amplitude, and then of course is degenerate with these multiplicative systematics. But this is an ongoing analysis and looks promising as a way of showing how to do with what to do with this kind of cross correlations. Any questions on this part? Otherwise, I should move on to a different topic. Well, anyway, you can ask questions later. The next topic is about using these synergies to find some signal that is very low the noise level of what you are interested in. And this is done in the context of dark matter, in particular on the particle dark matter scenario. So in theoretical physics, WIMPs, weak interacting massive particles are what we think dark matter could be made up of. And in this context, you have dark matter particles that are not just, they do not interact only gravitationally, but can have weak interactions. Weak interactions on a scale that depends on the cross section. Now, in this context, you can have particles of dark matter annihilating or decaying into standard model particles like electrons, protons, or photons. And in this scenario, the mass of the dark matter particle, which is about GeV to TeV scale, will produce byproducts and products, that are in the same mass range. This means, in particular, in the case of photons, gamma ray photons. Now, looking for gamma rays that come from annihilation or decays of dark matter particles has been done by the astroparticle community. And this has been done, for instance, by the Fermi Satellite, which is a NASA satellite that has been looking for more than 10 years at the sky in the gamma ray. What you see here is the best ever view of the gamma ray sky. You can definitely see the plane of the galaxy here. And the bright spots that you see around are known gamma ray sources. The rest, this anisotropic sky that you see, is due to all the unresolved emission from all the sources that are below the detection threshold or the instruments, and possibly from dark matter annihilation or decays. Now, if you want to look for dark matter signatures in this picture, what you can do is looking at the flux of these gamma rays as a function of energy, so the energy spectrum. These crosses in black are measurements from Fermi, and these different colored lines are models of the unresolved emission from the main contributors, which are blazars, misaligned AGNs, and star-forming galaxies. And of course, these are models of unresolved emission, so we don't know them like for sure. And the error band around represents our theoretical ignorance about how these models, how much these models are accurate. And there is also some contribution from local, like galactic pulsars, but this is very subdominant. Now, if you also had a contribution from dark matter particles annihilating, for instance, you would expect to see a nice bump somewhere in the spectrum corresponding to the mass of the dark matter particle and at a level given by the cross-section. Unfortunately, the shape of this measured data is very well fit by a combination of power laws that are due to astrophysical sources. We don't see any spectral feature that could resemble the presence of dark matter particles. This could be due to, well, of course, being the low dark matter in the form of particles, or by the cross-section being just too small for this to stand out. So you need to resolve more and more sources to lower this unresolved curve down. Another way of studying this, though, is through, again, correlations. So you have your maps of the anisotropic sky. You remove all the resolved emissions. So you remove the galaxies, our galaxy, you remove the galaxies that emit in gamma ray, and then you take the cross correlation or the harmonics power spectrum of this. And in that by different groups, and this has been done here by us in this paper by 2013. And what you see here as a function of multipole is the autocorrelation power spectrum of gamma ray anisotropies, and this is the data from the Fermi Satellite 10 years ago, basically, with different lines showing the contributions from different models. So blazars is in red, star-forming galaxies is in yellow, and like some feasible models of the decaying or annihilating dark matter in blue and green. And the point is that from the point of view of the autocorrelation, blazars that are very powerful, very bright, but very few, contribute like a Poisson shock noise. And this is multiplied by L squared, basically. So that's why you see it's raising like L to the second power. And this model can just fit Fermi data by itself. So if you would ever want to detect inside annihilation of decaying of dark matter, you would need to lower down this threshold all the way down. So from this point of view, it seems like rather discouraging. But then we consider the fact that both the astrophysical emission of dark matter and any dark matter particle emission would come from the same underlying glass case structure. So we expect some level of cross-correlation between cosmological distribution of galaxies and these gamma ray observations. And then if you do this sort of cross-correlation, so this is the same, but the cross-correlation of cosmic shear from the distribution of galaxies in the in the universe, and gamma rays from Fermi, this is what you get. Again, this has been split in different colors, and now blue is the annihilating dark matter signal, yellow is star-forming galaxies, and red is lasers. And this is for the cross-correlation, a forecast for the cross-correlation of Euclid, shear, and Fermi, with the total signal in black with arrow bars. First of all, the signal in total seems to be measurable, at least on this forecast level. And now the really striking thing is that blazars that were completely dominating the signal in the autocorrelation phase now are completely subdominant. And there is the possibility, depending on the cross-section, that shifts this blue line solidly up and down to actually measure any dark matter particle signature. The way this cross-correlation blazer dropped is due to the fact that this kind of cross-correlation are able to single out the non-thermal emission that you expect from dark matter with respect to the rest. In particular, these blazars we said are the blazars we see around are very bright and very powerful. And the fact that we cross-correlate them with shear is a signal that prefers very massive halos, because you need a lot of mass to produce a lot of wavelengths. At the same time, similarly, you expect to have the most of the dark matter annihilation signal coming from massive halos, because you have the largest density, right? So you have the more dark matter particles that could annihilate. Whereas to be unresolved, these blazars have to be either very far away, or they have to reside in very small halos, because otherwise they would have been bright enough to be measured above the detection threshold already. So this means that this cross-correlation prefers dark matter, and to some extent also clustering from some star-forming galaxies that are a lot with respect to blazars, which are the contact. So this is the reason why there has been this complete flip in this picture. The beam, Fermi beam is quite bad. So it's above 1 degree on very low energy.
Will you give us an estimate of the cross section?
So people are looking, this is people are looking at dark matter particle cross section, like velocity average cross section of about 10 to the minus 23 centimeters squared per second, centimeter cube per second, which is what you would expect for the so-called WIMP miracle to happen. At the moment, we have only bounds from indirect dark matter searches in other cases. And from this kind of cross-correlation, we are able to put bounds on non-detection of the signal with different combination of class phase structure data sets, clustering of galaxies, cosmic shear, clustering of clusters even, and the unresolved gamma ray background, this UGRB, in different years. And in this plot, this is the usual plot that is shown by astroparticle physicists, where you see the cross-section for dark matter particles, sorry, 10 to the minus 26, as a function of the mass of the dark matter particle. This is a thermal cross-section, so what you'd expect in the WIMP miracle scenario. And these are the bands. So this band here in gray is what was put on from the autocorrelation of gamma rays itself. Then with different analysis, we're able with shear from KIDS to put a similar, KIDS is another cosmological experiment for cosmic shear, like stage 3 compared to Euclid, which is stage 4. We're able to put similar constraints. And then these were these are different forecasts for a future possible, well, now and has not been adopted by ESA, but this was Astrogam was a space mission for low energy like MEV gamma ray emission. And this comes from an analysis that we did in collaboration with the Dark Energy Survey in 2020 on the cross-correlation. This also came the first detection of the cross-correlation between shear and gamma rays. You see the gamma ray sky in black below, and you see the shape of the footprint of the Dark Energy Survey in dashed line. And in particular, these pink areas are areas where in 2020 we had year 1 data from the Dark Energy Survey, and we did this cross-correlation between the gamma ray maps and Dark Energy Survey shear, and we were able to get a 5.3 sigma detection of the signal, which would, in principle, translate into bounds on dark matter particle properties, which are like parameterized in some way. So, of course, this is just about the measurement of the signal itself. It's not a claim that we measure dark matter with a mass of about 100 GeV to this detection level, because of course this was done for one single channel in annihilation, so you would need to span all possible branching ratios, etc. But this is to show that the technique is actually working, and we are now analyzing year 3 results, so the final year 6 result. So the final difference of the Dark Energy Survey. Is it? I guess it's about. Okay, then if I can quickly guide you through the last of these ideas, which is how to use synergies to beat cosmic variance. It's actually a quite nice idea. Cosmic variance, as I told you, is about the fact that we are measuring only one universe, right? So if you want to measure statistical significance on something of very large scale, you have only a few independent modes. But the idea of using all the information together, what is called the multi-tracer analysis, was proposed by Uros Seljak back in 2009. And it's about the fact that, yes, the distribution of traces of the large-scale structure, right, galaxies that reside in the potential wells of the dark matter structure, this is stochastic. But their evolution and the large-scale properties, like the bias, they are not stochastic. They are, to some level, deterministic. So if you have if you can cross-correlate and take auto cross-correlations of different populations of tracers, for instance, with known biases and with known properties, it's like having, in a sense, twice another realization of the same underlying fields with the different traces. So if by putting all this together, you can, in principle, this was shown, was proposed back in 2009 to beat cosmic variance to a certain level. I mean, theoretically, if you do like a back on the envelope calculation, you see that the covariance of your data becomes singular. I mean that you have perfect knowledge. It's no more deterministic. Of course, like devils in the details, so it doesn't work 100%, but still there's room to improve. And in this case, you can do it in the context of galaxy clustering. So again, you're measuring the position of the number density of galaxies relative to some average at a given redshift. From perturbation theory, we know that this is related to some extent to the overall density fluctuations in matter, which is the standard, the main contribution. But there are other terms that come, from instance, from velocities, the fact that we are not measuring galaxies in real space, but in redshift space. So redshift is also related to velocities, and we need to disentangle this information. And on top of that, position of galaxies are also distorted by lensing, right? So we have to take these other effects into account. And plus, we are not really measuring any cube of universe at a given time. We're measuring galaxies on the past light cone. So we are projecting this cube onto the surface of the four-dimensional light cone where light photons travel towards us. And this is what is usually referred to relativistic corrections, which are very minor, very minute, but actually these are extremely important because if we were ever able to measure these relativistic distortions on cosmological scales, this would be a confirmation of general relativity in a regime very far away of the strong gravity regime that I was talking about at the beginning of my talk. Now, usually galaxy clustering analyses are done considering redshift space distortions, which is something which is related to velocities, again, and the density contributions. But the other contributions are lensing, of course, and relativistic effects. The most important of these relativistic effects is relativistic Doppler, which is again due to velocities, but in a different way with respect to redshift space distortions. Now, this delta, so the density contrast in number counts of galaxies, is related to the underlying matter density contrast with a bunch of terms. And the most, the classic term that you consider is linear galaxy bias, at least in the very large scales. Then you have redshift space distortions that enter through the growth rate, which is f, and mu, which is a cosine of the angle between the direction of the k vector and the line of sight. This is because redshift affects the position of galaxies only along the line of sight, because if galaxies are coming towards you or going away from you, not if they move in another direction. Then the most important terms in terms of relativistic effects is Doppler, as I was saying. Doppler enters with a specific magnitude that depends on the type of galaxies you're measuring, so it depends on the sample that you're using. Again, it enters with the growth. It's only linear in this cosine of the line of sight. And there are two other very important things. It's in Fourier space, it comes as an imaginary contribution to the power spectrum, and it comes with a conformal Hubbard factor over K dependence. K is the wavelength, the wave number of the perturbation, meaning that this term is important only when K is very small, of course. And K very small means very large separation, so very, very, very large scales. And large scales are affected the most by cosmic variance, because it's where you have the fewest modes available. Then this is important for relativistic corrections, but also if you had any type of non-Gaussianity from inflation, you expect the bias of traces to gain a scale dependence. So the bias of your, you can parameterize this non-Gaussianity in the sense that the bias of your galaxies, the same bias you would have in a just Gaussian universe, plus some stuff proportional to this amplitude of non-Gaussianity, FNL. And the way it scales with scales is h over k squared. So this is important in even larger scales. Just to give you an idea of how this works. So the matter power spectrum at redshift 0 is here depicted in blue. Then you add some bias for certain galaxy population. This is just a toy model where bias equals 2 or something like that. The redshift space distortion along the line of sight adds some power on top. And then if you had Doppler, you would see this 1 over k contribution kicking in here. And if you had non-Gaussianities, this would further go like this. Now, at the moment, data from galaxy redshift surveys haven't managed so far to measure not even the turnover of the power spectrum because of volume, because of system. So if we wanted ever to go to so real scales, we really need to have a really big volume available. This is a plot from, I forgot the reference, but from the SKA White Book back in 2015, where you show the volume of of galaxy surveys as a function of redshift. You see Euclid here in the redshift frame from spectroscopic galaxies. SKA galaxy survey and this new method of measuring clustering of traces with the SKA through what's so-called intensity mapping for neutral hydrogen. So there is room to do this in both experiments and in particular in cross-correlation. And in this preliminary analysis with my student Federico, we did this analysis as a function of the diffraction of the sky that you have at your disposal to measure the Doppler amplitude in relativistic, the relativistic Doppler amplitude as a function of the redshift at your arc. So this is not cumulative. The fact that it increases just shows you that at low redshift, the volume is smaller, and then the further you go, the deeper you go, the more volume you have at your disposal. But then again, there is cosmic variance. So you gain because you increase the volume, but then these curves flatten, all of them, they're almost just rescaled, not exactly, but almost just rescaled. So let's just focus, for instance, on the curve that shows you this half of the sky, right? You see that you increase the volume, so your measurement, the detection significance. Sorry, this is not the marginal error. This is wrong. What's on the y-axis is the detection significance. So the chi-squared versus the null hypothesis of no Doppler, right? So you want a large number on the y-axis. Is the reverse of the marginal error. I changed the plot at some point and I forgot to update the label. So you see that the detection significance increases as you go up, as you go deeper in redshift, but then it flattens. And this is because even if you had a huge volume available, the number of modes are still very few. And so you're not able to extract any more information basically on this relativistic effect. Now, we did another exercise on, instead of using all galaxies available by using different samples, like faint galaxies and bright galaxies, it could be from Euclid and SKA or within the same experiment. And there is, since this Doppler effect depends on the galaxy population that you're looking at, it might be useful to have either very faint or very bright galaxies, even though they have very, very large shot noise term compared to having all galaxies together, because we are interested in a regime which is not affected by shot noise. We are looking at the very, very, very large scales. So shot noise kicks in on small scales in this sense. Still, you gain even an order of magnitude, which is not less, but the cumulative, sorry, not the cumulative, but the differential detection significance is still below 1, it's like 10% or something. So there's no detection. It's 0.1 sigma detection, which like arguable. But now, if you do the cross correlation between these different population of galaxies, you have a massive boost here. And the reason why you have this massive boost comes from this expression. When you take the modulus squared of this object, so you have the power spectrum, of course, the complex term disappears because you have delta complex conjugates, and there's no complex term arising. So in the power spectrum, these effects enters as k to the -2 because it's the square of the term. If you take the cross correlation between two different traces, traces A and tracer B will have a different bias and a different amplitude for the Doppler. So in the cross correlation, you have a imaginary term which is linear in 1/k instead of being quadratic, meaning that it's in at much smaller scales with respect to the autocorrelation. And this is the real reason of this huge improvement in detection significance, which makes it probably measurable. And now, if you're clever enough and you select galaxies, if you tailor your galaxy samples in a correct way, you can have a further jump. And this jump is not, I mean, I didn't just cut and paste like higher. The jump comes from the analysis. I just cut and paste another plot to put it on top. But this is the actual, I mean, this is the level here is correct in the analysis. Right? So this is actually very exciting. This is something we're working on at this very moment. And I really look forward to something more in the context of real Euclid and real SKA. So this is all. Conclusions. First of all, thanks for bearing with me till now. The take-home message I want to convey is it's a really great time for cosmological synergies. It's not just like a punchline for some advert, but we are really getting into it because SKA is being built at this very moment. We are having the first ever intensity mapping data for neutron hydrogen for clustering analyzed in the past couple of years. Euclid is going to be launched in the first week of July. So in the next year, we could really apply all these techniques to real data, to the best ever data we have had in cosmology. This cross-correlation will be crucial at the very basic level, at least to cross-check the validity of cosmological results. Suppose you measure dark energy different from cosmological constant, that will be like a Nobel Prize thing, right? But you want to be more than watertight. And measuring it in a completely different setup with a completely different wavelength is a way of, it's like CERN with the Higgs. You had two different experiments, Atlas and CMS, doing exactly the same thing for such a discovery, like a momentum discovery. And then on top of that, you can use this cross correlation to remove or at least alleviate contamination from systematic effects, as in the case of cosmic shear between radio and optical. And finally, you could even access signal. You can actually, we did it already. Access signal that is buried either in noise or cosmic variance for other fundamental physics tasks, like for particle dark matter or for understanding gravity and cosmological states. That's all. Thanks a lot for your patience.
Yes. How much the lensing of the CMB affects the results?
Which one? For all of them, lensing CMB at the moment, we actually use CMB lensing as a signal in the cross correlation with gamma rays. So the first detection actually of the gamma rays cross correlation was done with CMB lensing, and it confirmed that this unresolved emission has to be extragalactic because it correlated with CMB. But for the rest, the scales are quite different, and we can use CMB lensing as a probe instead of as a contaminant. So that's
very impressive. I have a question from a strategic point of view. People have put forward the self-interacting dark matter scenario to resolve problems against arguments like the diversity problem or the transport problem. And they usually involve a cross-section per particle mass on the order of 1 centimeter squared per gram. Does it mean that we can rule out these kind of models with your results?
No, because they are these are model dependent. So these are all these analyses have to be done on a model by model basis and then marginalizing over all the model parameters. So in this sense, there are different ways of tackling the same problem, but the self-interacting is a different scenario in this sense. So this goes into the direction of having direct dark matter searches like Grassasso, Dama or Lux, all these experiments also in Japan and elsewhere. For direct detection, indirect detection from astrophysical, astroparticle physics data, and possibly production in accelerators and colliders, creating high energy events where some missing energy will be what is left over by a particle of dark matter. So in the context of self-interacting dark matter, you can devise some different cross correlation, but you have to think carefully about what model you want to test.
So self-interacting dark matter scenarios have parties that collide, but they do not annihilate.
Yeah, exactly. It's a different sort of annihilation. Or of interaction.
Okay. I have another question. But there is no answer. That question is how the CMB dipole affects your errors. Because there are some people like some guy from Oxford, but they have found some results that the CMB dipole is different from the one that you measured.
Yeah, that's true. So all these analyses about clustering, I keep forgetting whether I used one or the other, but all these analyses about clustering and harmonic space mostly always don't consider the dipole. So you start from at least L equals 2. Because the dipole per se, it's mostly not cosmological, but due to our motion. Yeah, what is actually very interesting about the dipole is that it can tell you something about the cosmological principle and the Copernican principle. So in the radio, so I didn't talk about this, but in the DSPSKA, in continuum galaxies, particularly because with continuum galaxies, a very large number of galaxies down to very high redshift, meaning that you have a huge volume that you can measure. You don't have the position of the galaxy radially, so you can't do much of this, radial tomography. But you can just measure the overall properties of this galaxy distribution. And one of the things people have done and want to do is about the dipole of the last phase structure. And data at the moment don't agree with the CMB dipole. I mean, you can try and go around them in many ways, but still the amplitude of the dipole mostly. So one of these, the most used surveys, NVSS, that has found an amplitude which is slightly different from the CMB and not compatible, at least at a few sigma level. It's not a huge discrepancy, but it's like a 2 sigma. A much larger discrepancy is from the TGSS, which is a radio continuum survey, That one has been analyzed in cross correlation with some of these data as well, and seems to be non-genuine, so due to some systematics in that sense. So that the very large amplitude and wrong orientation of the dipole in the radio from TGSS seems to be a problem of, like calibration or the instrument. But there are other cases where you can see this difference. At the end of the day, the dipole is related to the Doppler that I was talking about. Yeah. And so in principle, what I've been arguing is that the amplitude is also related to this alpha term that depends on the evolution bias and magnification bias of your sources. So you should take, we should take this into account, which hasn't been done so far. So that might account for some of this. This is one of my, I would like to work on that, but in principle, you could actually work it out pretty easy because it's a linear effect, right? So you know how it should work.
Now, points from the observations point of view, because have you ever considered the error bars that you have from the velocity and the shear position and so on?
Well, yes. With shear, we know, this is the kind of forecast we've been doing for Euclid, etc., are calibrated in simulation with the data we know at the moment. We know that error, like shot noise from shear is not just flat as you would expect at 0th level, but still it kicks in at different scales with respect to this. For velocities, if you measure the distribution of galaxies per se, so if you do clustering with the position of galaxies, you measure velocity through the position, so that's not a main problem. Another nice thing that you could do with SKA is measuring the velocity power spectrum. So measuring directly the power spectrum of the velocity perturbation through an estimate of the velocity of the galaxies. That's actually very, very interesting because theoretically, if you think of it, the main tensions we have in cosmology at the moment are on H0, which is the only parameter in the cosmological model which has units, or the other are dimensionless. And if you want to measure H0, you can do it very well with CMB, and CMB has units. Galaxy clustering is dimensional, so it's intrinsically can't tell you much about that. Velocity power spectrum is different because it has units. So I see like a lot of promising things that you could do in that sense. But velocity error bars on the velocity power spectrum are much larger, and we only know them well at very low redshift. You could use Tully-Fisher, but the error bars are huge, or supernovae, but it's very low current sparse. But it's another possibility.
If this analysis is dependent on your
no, the model dependence in that is twofold, but it's not on the maps themselves. It's always model dependence in the sense of you need to assume a model for your dark matter particles. So depending on whether you want to study decaying or annihilation of dark matter particles, the data is the same, of course, but you need a different analysis for the dark matter particle model, and it's very much model dependent for the astrophysical emission. So all these shapes will change your actual the data vector, because they enter in the amplitude, but they also enter in a subtle way in the clustering, because you need also to know the clustering of these unresolved sources. So you, like in the context of halo model for a scale structure, you need a concentration, halo, mass, and luminosity relation for these emitters, and you have few of them in the gamma rays, and you need to scaling laws to translate this into redshift and masses. So it's convoluted. And we try to model this, to take into account this with nuisance parameters in the analysis. It's not everything fixed, but still, nuisance parameters are model dependent in a sense that you need a model that fits with those parameters. It might not be in the fiducial value, but still you need the structure to be that.
Could you tell where is the intrinsic alignment of galaxies
Yeah, they don't. No, this is done only for, let's say, instrumental systematics. So miscalibration, which sends some sort of a multiplicative systematics or residual noise or things like that. Intrinsic alignment, I mean, we did study it in the paper, I didn't discuss it here. It's a further additional systematics that you have here. It's a theoretical systematics, so because it's due to the fact that you're lacking some theoretical insight on how to model the intrinsic alignment of galaxies per se. It's a double-edged systematics, though, because it also contains cosmological information. Because the clustering of those galaxies and the way the tidal fields create these alignments is cosmological. So if you could model them, that would be like a level up, because then you can start extracting information. There is some gain that you have in this cross correlation, because the way these galaxies will be affected by intrinsic alignment is different. Most of the Euclid galaxies will be sort of the red galaxies or elliptical galaxies, which you expect to be correlated radially with respect to a potential well, like the center of mass of the halo, which like removes lensing from the signal, because with lensing you have with lensing you have this sort of tangential alignment of galaxies. With elliptical galaxies you have radial alignment, so you remove some of the signal. With the SKA you have spiral galaxies mostly, that they align through the to the radial momentum, the angular momentum of the galaxy, which makes them align effectively in the same way. So if you do analyze them at the same time, you have intrinsic alignment that enter in different ways. So you could do another sort of multitracer for this.
So it's very interesting to see all these survey and different groups and we use together. But all of this has been done with solar statistics, right? So everything that you have shown here was based on the second order statistics.
Yeah, it's 2-point functions.
And we know that we have enough information as soon as we are not motion, which is the case for intensity, for the intensity and everything. So what are the limitations of moving higher order?
The limitations is your imagination, in the sense that given that you have multiple things to cross correlate, the limitations is mostly the sheer amount of possible cross correlation that you can have access to. So not really a limitation. There's a huge range of possibilities that you have, and you need to choose what you want to do carefully, because doing everything is probably unfeasible at the moment, at least from the point of view of sheer computational power of time or something like that. But like at the level of standard endpoint statistics, not going into more modern techniques like the things you are doing, even the bispectrum, so the 3-point function, you could now take the cross correlation between 3 different traces or 2 of one kind and one of the others, and they have very different ways of entering. So for instance, intensity mapping is a powerful way to do very good radial resolution, because you measure the redshift perfectly at the cost of having very bad, not very bad, angular resolution. This could be done to recover some information for photometric galaxies, for instance, that they are the other problem the other way around. But the way you want to do this is, for instance, correlating 2 traces in photometric clustering and 1 intensity mapping, because you just get the most of the slicing due to intensity mapping. If you did the other way around with 2 intensity mapping traces and 1 galaxies, you have the problem of foregrounds propagating in intensity mapping propagating into the signal. So this was like for simplicity concentrating only in 2-point function, but really there's a lot of things to do that have not been done yet on high order statistics and also simulations we have for that.
Okay, so I think we should stop here. Let's thank
you.